Hi, this is chapter 6, and we're talking about forces that impact horizontal movement of air. And as I said to you before, this is a surface map of the horizontal movement of air. And as you can see, we've got pressure gradients here that are supposed to move across the isobars. Remember, from the high pressure out to the lower pressure. It should go directly across, but it doesn't. It's skewed. And it's not skewed just by a force of friction, which would be holding it back. It's skewed on a curve. And it's actually skewed by what's called a fake force. I'm going to look into that as a review. This is from our Wednesday lecture. You know that the leaf in Forrest Gump was acted on by Newton's laws of motion. The first law is an object at rest tends to stay at rest, an object in motion tends to stay in motion unless there is a force opposing that motion. And the second law of Newton's laws of motion talks about that force. That force is mass times acceleration. Well, what's acceleration? Acceleration is a change of speed. That makes sense. Acceleration could also be a change of direction. Remember, acceleration is a vector. And there are two types of forces that impact the leaf in Forrest Gump at the beginning opening credits. There are true forces acting on that leaf, and there are fake forces acting on that leaf. And fake forces are only seen in accelerating systems. We're going to explore that a bit more. But let's talk about the true forces. The true forces act on the entire vector of acceleration. They act on speed and direction. An example of true force is gravity, or pressure gradient force, or friction. You can stop this video and go over some of the reasons that these affect speed and direction. Then there is another type of force that affects that leaf in Forrest Gump, and that is a fake force that's seen only in accelerating systems. It acts on the leaf's direction only. It does not act on speed. So it is not acting on the entire vector. That's why it's called a fake force, because true forces act on the entire vector of direction and speed, and these fake forces do not. Examples of accelerating systems that employ fake forces are things like cars, and we'll go over that in a second, and airplanes and spaceships and elevators, and amusement park rides, because you know that this accelerates from being down low and going slow. It accelerates on an angle and going in very fast speeds. And for us, winds are examples of accelerating systems. Some of the fake forces in accelerating systems are things that you know. You know that the only reason you don't fall out of this ride is because of centrifugal force that plasters you against the outside. You know that when you're in a car and you take a turn at too high a speed, you're employing centripetal force, and it kind of makes you move into the curve. You lean into the curve. You know about G-forces. You hear about them in rockets, and they pull everything back. Though you're going forward at a fast rate, it pulls your skin back. It pulls you back. We are going to explore the Coriolis force for winds. And the Coriolis force is actually related to these artillery guns. The Coriolis force was really only understood well in World War I, where suddenly we were now employing artillery that could go miles and miles. That was never available before. And suddenly when they would point it right at the direction where they wanted to go, it never ended up there. It ended up to the right. And no one understood this until they studied the Coriolis force again. We're going to study it. I told you that this impacts direction and not speed. I went over that. If you want to stop the video here and take a look at this, it's a good idea. There's three analogies for this Coriolis effect, this effect that changes the direction of artillery. The first is the analogy of a cloud racing ahead or a cloud racing behind or falling behind. That is pointed out in this video. It's an excellent video for the first 1 minute and 20 seconds only. Please only watch it through there. It's a great video and a great analogy for those first minute or so. The rest is incorrect science. That's pointed out in the comments. But you can't beat the first minute and 20 seconds. The second analogy is in this Khan Academy video that I recommend. Just stop the video and you can probably copy this link and then employ it. And then the third analogy is an analogy that I have for you on the next slide of a moving sidewalk in Newark Airport. So I really hope that you will look into these videos because they're very helpful. This is my analogy of the moving sidewalks at Newark Airport. So they're flying past you and you decide, I have got wet paint on my feet. I've got to get rid of this wet paint. And the bathroom is on the other side of the moving sidewalk and I've got to get there to wash off this paint. So you go trooping over to walk right across the moving sidewalk. Oh, and guess what? Guess what? You don't move directly across the moving sidewalk. You actually get deflected off to the right. And your wet footprints give you evidence of that. This is very much what we're noticing with the Coriolis effect. Make sure you look at the videos so that this analogy sticks in your head. And make sure you stop the video so you can take a look at this analogy as well. This fake force impacts the direction. It deflects it to the right. It does not impact the speed. And it is due to the rotation of the Earth. In the northern hemisphere, it deflects objects to the right. In the southern hemisphere, it deflects objects to the left. So if you are starting out near San Francisco and flying to New York, your airliner needs a correction to correct for the Coriolis effect and get you to New York. The stronger, in our terms, in terms for us, the stronger the wind that we're talking about, the greater the deflection to the right. The amount of deflection depends on the altitude above the surface friction layer. It also depends on the latitude that you're traveling at and how long a distance you're traveling and how high a speed you're traveling. That's why the jet makes a great example. Another great example are ocean currents, because again, they travel long distances just like the jet, and they travel higher speeds relative to the speed of the ocean around them. That's why the Gulf Stream deflects to the right. The Canary current comes down from the North Pole and deflects to the right. And you can take a look at those in the Southern Hemisphere as well. So what this means for surface maps is that instead of taking from the high pressure to the lower pressure and going directly across the isobars, you're actually skewing this to the right. And what I wanted to say was that that's because you're moving out of the high pressure centers. You're actually, in some areas, forming a pretty tight gradient and moving faster across the tight gradient. You're combining with centrifugal forces that are pulling you out as well. But you're competing with frictional drag, which is pulling you back. So while the centripetal forces pull you out, the pressure gradient forces pull you out, the frictional forces pull you back, and this Coriolis force pulls you to the right. The combination is a weak move and a weak deflection to the right. On the lows, you have an even weaker deflection to the right that you really don't even notice very much because it's being pulled into the low. The reason you don't notice this right deflection so much around the lows is because you're being pulled into the lows like you'd be pulling into a centripetal force that is combining with frictional drag. Because when you're being pulled in, you're slowing down. That motorcyclist is slowing down around the curve as he's being pulled in. So while you would go into the low and go across the isobars, you're also being pulled into the low by the centripetal force, and you're being slowed down by the friction. So you're not noticing very much of a pull to the right. It's there, but it's not as big a deal as around the high pressure systems. Hope that you'll take a look at all of this, and I hope that we get a chance to talk soon. Thanks.